Hello everybody, and welcome back to your grandma's favorite math channel, Bo Math. That's right, today we are back and better than ever, because today we're going to be doing some practice on the last video. What did we talk about last video? Well, if you don't know, you better go and watch it. But just as a little recap, we essentially just discussed a new perspective on some of the stuff we already knew. We talked about how we could kind of think of the opposite of a number, right? We could think about the opposite of 5 as -5, but that was in the additive sense. We also saw that we could think of the opposite of 5 as a fifth, and that would be in the multiplicative sense. So there's kind of different ways that we could think about the opposites of numbers, and we saw that by thinking about the opposites of numbers, we kind of were able to kind of merge subtraction and addition into the same kind of thing, and we were able to merge multiplication and division into the same kind of thing. Furthermore, we talked about different identities for addition and multiplication, which were 0 and 1, and how they have a lot of really nice properties. And the overarching theme is that the whole structure of how numbers work with addition very much paralleled the structure about how numbers work with multiplication. So today we're going to be just getting more comfortable with that idea. I've got 5 practice problems. I'll be showing them to you on the screen right now. So as always, pause the video at each of the problems, try them out for yourself, and then we're going to go through the answers together. Alright, let's get going. Question 1. So question 1 says, find the additive inverse and the multiplicative inverse of each of the numbers. Alright, so we start with 3, and to find the additive inverse, all we have to do is we have to just apply a negative to the number. And that's because if we're thinking about 3 as an addition or as a shifting, the opposite of 3, which is going to be moving us 3 to the right, would be moving us 3 to the left, and that's captured by its additive inverse, which is -3. To get 3's multiplicative inverse, well, if we're thinking about 3 in the multiplicative sense, that's going to be stretching our number line out by 3, right? So the opposite will be, instead of stretching it out, it'll be stretching it in or compressing it. And to do that, that's essentially division by 3, which is the same as doing the reciprocal of 3, which is 1/3. For part B, we are dealing with -5 now. So the additive inverse, which I'm just going to abbreviate now as AI, not ChatGPT. The additive inverse of -5, well, that will be us applying another negative, right? It's always just applying a negative, but 2 negatives make a positive, right? So we just get to +5, because the opposite of moving 5 to the left, which the -5 embodies, and we know we're shifting because we're dealing with this in the additive sense, the opposite of that is just going to be moving 5 to the right, which is +5. And now when we're talking about 5 in the multiplicative sense, so now we're viewing 5 as a stretching, well, we take the reciprocal of that once again, right? So the reciprocal of -5 is going to be -1/5. We could just think about -5 as -5/1, and then we're just taking the reciprocal of that, right? So now we have a fraction here, but this is just a positive number. So when we think about it in the additive sense, it's still just a shift. It's just a shift by a really small amount. So the inverse is just going to still be the negative version of that, -2/81. The multiplicative inverse of this, once again, we're just doing the reciprocal of this, right? Because the 2 is basically a stretch, the 81 is basically a compression. So to do the reciprocal of that, that turns the compression into a stretch and the stretch into a compression. We've talked about that in depth in the division video. But what we end up getting is we end up getting the reciprocal. So we get 81/2 is the multiplicative inverse. And for part D here, I think you're kind of getting the idea. The additive inverse, we have a negative number, so the additive inverse will be the positive version, right? Just in the opposite direction. And the multiplicative inverse, well, once again, that's going to be the reciprocal. So we're going to get -2/5. Now, one comment on taking the multiplicative inverse of -5/2. We could say, okay, -5/2, and then doing the reciprocal of that, if we flip this, we get 2/5, right? So we're literally just keeping the negative attached to the 5 this whole process. But the thing is that a negative divided by a positive is negative anyways. So we can write -5/2 as just -5 over 2, where the negative is just kind of in front of this and it's not necessarily attached to either the numerator or the denominator. And similarly, this over here, once again, we have a positive divided by a negative. We know that that is negative overall. So we can just kind of take the negative out to the front, and it's going to give us the exact same result. So when it comes to kind of taking the reciprocal of negative numbers, it doesn't really matter where you put the negative. As long as there's just one negative there, be it in the numerator, denominator, or just outside the fraction, it all represents the same thing. It's a fairly simple idea, right? Either just applying a negative or taking the reciprocal. We've just kind of attached the concept and the terminology of an additive inverse and the multiplicative inverse to these ideas. But if you want some extra practice, choose any number you want and find its additive and multiplicative inverse. And for some even more practice, can you find a number for which you can't take either its additive inverse or its multiplicative inverse? So maybe you can find a number where the additive inverse just doesn't exist somehow, or maybe the multiplicative inverse doesn't exist somehow. We will talk about this in a later video because there is actually a number like that. But for the time being, I'll leave it to you to see if maybe you can discover it for yourself. If not, that's fine. It's going to come up later down the road. Question 2. All right, question 2 says, explain the significance of writing subtraction as the addition of a negative instead. So, for example, we know that 3 minus 2, that's the same thing as 3 plus negative 2. But just because we know they're the same, the question is why would we ever want to write it in this more complex way? And we discussed this in the video. This allows us to take the perspective where we view the plus as the instruction to think about this next number as a shift, where we put all the power on the number to determine how we're doing the shift. So the 2 tells us that we are moving in 2 units, and the negative tells us the direction we're going. So it tells us that we're going to the left. 2 units to the left, and the left is specified by the negative part. To contrast this, 3 minus 2, we still knew it was a shift, but the fact that we were going to the left wasn't encoded in the 2 anymore, it was encoded in the operation of the minus sign. Alright, so we saw that this just gave us a different perspective where there's less power on the operation and more power on the number to determine what we're actually doing here. Question 3. Alright, question 3 says, show why it is impossible to have any number other than 0 be the additive identity. So we found in the last video that 0 had a lot of nice properties and we called it the additive identity. But is it possible for a different number to be an additive identity? Right? Like, why does 0 necessarily get to be the only number that has all those kind of nice properties we had? And kind of the main property we had for 0 to be the additive identity is that when we tried to take the additive inverse of 0, right, just by applying that minus, we ended up getting 0 back itself. So now the question is there any other number that does that? And if so, maybe we should also consider that to be the additive identity. Well, it's not going to be possible. And we can reason it as follows. Alright, so suppose we have a number other than 0. Well, that means it has to be either positive or negative, right? There's no other option. So let's kind of consider both of these situations. So if it's positive, its additive inverse will become negative, right? Because we're applying a negative to a positive number. And if it's negative, well, we're applying a negative to a negative, so it's going to become positive. But in both of these situations, if we start with a positive and we end up with a negative, that's not the same number that we started with, right? And similarly, if we started with a negative and we end up with a positive, that's a different number from what we started with, right? Because you can't be both negative and positive at the same time. So what this means then is that this number, since it wasn't 0, when we took its additive inverse, it became a different number. And that means it doesn't have the property that we saw 0 does, which made it the additive identity. So since a positive doesn't equal a negative, this non-zero number, right, the number we started with, can't equal its additive inverse, and thus it's not an additive identity. So notice what we did to show that it was impossible is we looked at every single possibility, right? the number is either positive or it's negative if it's not 0. And we showed that regardless of the possibility we chose, it was not going to be an additive identity. So we know for a fact now that 0 is really special. It's the only number with this property. Question 4. All right, so question 4 says, show why it is impossible to have any number other than 1 be the multiplicative identity. So this is kind of similar to question 3, except there's going to be one little caveat. And that might be that if you're trying to do a method similar to question 3, you might end up in a situation where you're trying to basically show 1 is the only number whose reciprocal is itself. And indeed, 1's reciprocal is itself. However, it's not true that it's the only number whose reciprocal is itself. Let's take -1, for example. -1 is -1/1. But when we take the reciprocal of that, that's 1 over -1, but that is still -1, right? So -1 is actually also its own reciprocal. However, it's not the multiplicative identity. And so this is where I made a little bit of a mistake in the last video. I did leave a comment on it, so you can check that out as well, but I'm going to just quickly address the mistake. So the mistake is that I said that the multiplicative identity was basically determined by the fact that it was the only number that when we took its reciprocal, we got itself. Right, basically the only number whose multiplicative inverse was itself. And while that's a property of the multiplicative identity, it's not what defines it, because we see that -1 also has this property. So the defining property of the multiplicative identity is actually the fact that anything times 1 is itself. That was one of the properties we saw, the multiplicative identity, but that's actually the defining property of it. That's actually what makes it unique. Nothing else will have this property. So you might think, okay, did I also define the additive identity incorrectly? Because I said that the additive identity was the only number whose additive inverse was itself. But in that case, and as we just showed in question 3, that is actually true. There's no other kind of hidden, there's no other hidden surprises in there that could be messing with us. So this is true. So this turns out to be an equivalent way to define the additive identity, but we can also define the additive identity as being the unique number where anything plus that number, 0, is itself. And this is also the only number with that property. So we do see we still get kind of this analogous properties and an analogous way to define the multiplicative and additive identity. So hopefully that clarifies it. I apologize for any confusion. But now that we have that in mind, how can we use this property of the multiplicative identity to actually establish that it's impossible to have any number other than 1 have this property, where anything times 1 is itself? Let's say, for example, we took something that wasn't 1. So let's say 2, for example, right? And if we take anything and we multiply it by 2, if it did equal itself, well, since we get itself for both of these, and we're doing anything times 1 and anything times 2, and we get the same thing, doesn't that kind of entail then that 1 has to equal 2? But that's obviously not true, right? 1 doesn't equal 2. So this is what we call in math a contradiction. And if we reach a contradiction, that means we did something wrong, basically, right? For example, if I'm doing, 3 plus 5 minus 2, and I say, okay, 3 plus 5 is 7, and I subtract 2 and I get 5. But then someone over here says, okay, 3 plus 5 is 8, minus 2, I get 6. Well, 5 doesn't equal 6, right? So that's a contradiction. That means a mistake happened somewhere, right? And the mistake is that I said 3 plus 5 was 7, right? So essentially, we made a mistake somewhere. But the mistake didn't come from anything in here because we know anything times 1 is itself. So the mistake then had to come from saying anything times 2 was itself. So this has to be a false statement. So similarly, if we take any number in here that's not 1, right, like 3 or a half or -75, then anything times that number, if we claim it's itself, that's going to be basically the same thing as claiming that number that isn't 1 equals 1. But that's a contradiction. That's a false statement, right? obviously if it doesn't equal 1, it can't also equal 1, right? So in that sense, we've shown then that 1 is the only number that can actually have this property.
Question 5.
All right, so consider 3 plus 5 minus 5. This is clearly 3, right? 3 plus 5 is 8. Subtract 5 again, we get back to 3. But explain why we get 3 using the properties of the additive identity discussed in the companion video. So we saw that the additive identity, or 0, had several nice properties. I'll list a few of them now. So we noted that anything plus 0 was itself. We saw that anything plus its additive inverse was 0. And we saw that negative 0, or the additive inverse of 0, was 0. So these are kind of 3 nice properties that we have to work with here. And we're saying, okay, how can I actually use these properties? So maybe I'll call it property 1, 2, and 3, in order to show that 3 plus 5 minus 5 equals 3. And again, this might seem kind of like a useless exercise just because we know it is 3, but so that we kind of get a good idea for the importance of these properties and using these properties, we're going to kind of peel back what's going on here by applying this perspective. All right, so which one of these properties do you think we can use at the moment? So anything plus 0 is itself. Well, we don't have a 0 here. So I would say that 1 and 3 aren't too relevant at the moment. But 2 looks like it could be relevant because anything plus its additive inverse is 0. And we have the additive inverse of 5. We have negative 5. Or we almost do. But we know we can rewrite this as 5 plus negative 5, right? And now we see clearly, hey, this is something where we have a number plus its additive inverse, and we know by property 2 that that is 0. So we can then say, okay, this equals 3 plus 0. And what I'm going to do is over the equal sign, I'm going to write a 2 there to show that we used property 2 in this situation here. And now that we've used property 2, we have something where it's 3 plus 0. But we know by property 1 that anything plus 0 is itself. So this then gives us that we get 3 because we have 3 plus 0. So we get the number back. We get 3 back. And this was by property 1. So again, this seems kind of like overly complicated, and in some ways it is. But again, the point of this exercise is to basically give you practice with using kind of some of these properties of 0 or some of these properties of the additive inverse. With that in mind, let's try and do part B, and it's a very similar idea except just using the multiplicative properties. So it says consider 3 times 5 times a fifth. This is 3, right? And we can show that this is 3. 3 times 5 is 15. Multiply it by a fifth, that's the same as 15 over 5. 15 divided by 5 is 3. So we know that's 3, but we're going to try and use the properties of the multiplicative identity, so that's 1. And we're going to try and show that this is 3 using those instead. So we know the properties are very analogous to this, but I'm going to write them out so that we can use them in showing that this actually does equal 3. All right, so we've got properties 1, 2, and 3 here. Very analogous, right? Anything times 1 is itself. Anything times its multiplicative inverse, it gives us 1, not 0. And the reciprocal of 1 is 1, or the multiplicative inverse of 1 is 1. Okay, so we're working with this expression here, 3 times 5 times a fifth. And we want to show that this equals 3. So which property can we use first? Well, probably property 2 again, because we're doing anything times its multiplicative inverse. And we know the multiplicative inverse of 5 is a fifth. So we already have a situation that's set up to work with 2. So what this then gives us is 3 times 1. Since 5 times a fifth by property 2 is going to equal 1. So we use property 2 here. And then we get 3 times 1. And we know by property 1 that anything times 1 is itself. So 3 times 1 is going to give us 3. So just like before, we used property 2 and property 1 just in the multiplicative context here. And we use that to show that this expression here does indeed simplify down to 3.
Concluding thoughts.
Alright, well, that's going to do it for today's video. I hope you found it useful and that you're feeling more comfortable with these concepts. I think this is an important perspective to get comfortable with because it does give a solid foundation for a lot of the different things that we're going to be doing in algebra, especially when it comes to things like simplification and dealing with very complex fraction expressions. And as we go on, I'm going to try and emphasize kind of why this perspective is useful in those contexts. But until then, you have yourself a good day, you stay groovy, and I'll see you in that next video.
F.O.A. Maths.